Good morning to all the participants present over here. For today's session, we have a very young, dynamic and talented speaker among us from Indian Institute of Technology, Bhilai. I would like to welcome Dr. Dhiman Saha sir for today's session. I will take two sessions on applied cryptography. Dr. Dhiman Saha is an assistant professor at Department of EECS in Indian Institute of Technology, Bhilai, and is also, as an additional affiliation, is an adjunct faculty member of Bharti School of Telecom Technology and Management, Indian Institute of Technology, Delhi. His qualification includes B in Computer Science and Engineering, gold medalist from NIT Agartala, MS in Computer Science and Engineering from IIT Kharagpur, PhD in Computer Science and Engineering from IIT Kharagpur, and is also the postdoctorate as visiting scientist from ISI, Kolkata. He has received several awards. Some are the Venus International Research Awards as Young Scientist in Cryptography 2019. He is the runner-up of the Best PhD Thesis Award in 2018, gold medalist in Computer Science and Engineering 2006 from NIT Agartala. His area of interest includes the symmetric key cryptography, quantum cryptanalyst, lightweight cryptography, cryptanalysis of hash function, authentication, and block ciphers, faculty analysis attacks. So I once again welcome and invite Dr. Dhiman Saha sir in our this 6-day induction program on cybersecurity and autonomy for the next session. So again, once again, welcome you, sir.
Thank you. Thank you, Dr. Shukla, and I thank you for inviting me in this cybersecurity and autonomy refresher program. And I think it's a very, thank you for the introduction. I think it's a very nice time to organize these kind of workshops because cybersecurity is something that affects all of us. So most of us may not be aware of it, that how much it affects us and how much in our day-to-day lives we are actually using cybersecurity. But we have to be, careful about this. So I think it's a very nice time to start this kind of program. I would request all the participants if they can mute themselves. Okay. So we'll be starting. So as Dr. Shukla has mentioned, we have this two sessions today, and the sessions will be basically on the field of cryptography. I'll be describing the two sessions are segregated in this way. And then the first session, we will be introduced to the the basics of crypto, and in the second session, we will be actually having some applied cryptography instances. So by this, what I mean is that we are going to spend in the first half about the theory a bit, and the second half we will see how it is going to get applied, right? So without much delay, I think I will start. As you see, our title of the talk is Cryptography, the Story of Alice and Bob, right? So why I'm telling this Alice and who are these Alice and Bob, right? Who are these people? So any talk on cryptography is incomplete without these characters. Okay, so cryptography encompasses, as I mentioned, it encompasses all of us. It's a field that affects all of us. So when I look at this slide, what I essentially see is a list of problems. Okay, and how these problems are captured by this slide, and that is what is interesting. Okay, for example, here the setting is that we have a character called Alice and a character called Bob, right? And Alice actually wants to communicate with Bob. Okay, that's a fine. That's a very normal scenario, right? You can communicate with this. These two people can try to communicate with each other. It's not an issue. But what is the issue here? What is the main problem that affects them? The problem is the channel through which they are trying to communicate, that channel is untrusted. That means you cannot trust this channel. Whatever information you are sending, it can be monitored by a character called Eve here, right? So Eve can monitor the communication. So it is as if someone can listen to whatever you are saying, right? So that problem needs to be solved. So can we communicate? Can Alice and Bob communicate in an untrusted environment without worrying about a character like Eve, who can actually listen to this communication or try to maybe modify whatever is going in this channel? Okay, so this is the basic setting of cryptography. This is a basic setting, and that is why we call it the story of Alice and Bob. So Alice and Bob want to communicate in an untrusted environment in the presence of an eavesdropper or the presence of an adversary called Eve. That is the basic setting. Okay. Now, what are the different problems that arise here? Let's try to understand that. What are the things that affect us? So, if in this slide we actually capture this through this in these 5 fingers that we have. The first problem that we are having is the problem of privacy. So let's get back to the picture and see what is the notion of privacy. Privacy means Alice wants to communicate with Bob, and she wants to maintain that the information that is being sent over this channel remains private, remains only accessible or understandable by Bob. Okay, it is being sent over a public channel. Okay, remember, we are not trying to hide the fact that Alice is wanting to communicate with Bob. We are not trying to hide it. The only thing that we are trying to do here is that we want to ensure that whatever is there in the message, that should be available or understandable by Bob and not someone like Alice. Okay, so this is the main. So this is the privacy of information. So it is only kind of useful to the person who is authorized to access it, or who is authorized, or for whom it is meant. Okay, so this is the basic setting of privacy, and I think all of us might be, we want to keep our communication private, right? For example, while before coming to this talk, you might have mailed someone, you might have sent someone a WhatsApp message, you might have called someone on a WhatsApp voice call. All this mode of communication that you have used today, or you might have accessed your mail just now. Everything that you use today, at this point of time, maybe someone of you are replying to a message to someone, some important message maybe. Whatever you're doing, even as at this point of time, this particular session, this talk that is going on, all are leveraging on this particular problem of privacy. We don't want people who are not authorized to access this, right? It is not like open, it is closed. So only people who have the link can access it, right? So here we are trying to maintain the privacy of information. So this is our first problem. What is the second problem? Second problem is integrity. Okay, so what is integrity? Let's try to understand what is integrity. So integrity means that Alice is sending some information, right, to Bob. Now it is going over a network that is untrusted, we mentioned. So might be possible that the character Eve tries to modify this? No, tries to modify, change something here, change something in this particular message, right? Is it possible? And if it is possible, then can it be detected? That is the question. So integrity means that the data as it originated from the source, has it reached the destination in the same form, or it was changed in between, right? That is the integrity of data. So the second problem that cryptography looks at is the integrity of data, right? What is the third problem? Third problem is authenticity, which is also very important. So authenticity is essentially something that Bob needs. Okay, so if Bob receives an information from Alice, can Bob be sure about the fact that it was sent by Alice and not by Eve pretending as Alice? This is the next problem, the problem of authenticity. So authenticity of the source. Okay, whether the information has originated from the place which it claims that it originated from, right? So these are the basic settings that we all have to be careful about. Okay, and then there are other settings also. There are we will not discuss them in this particular talk. We are mainly concerned about these three settings, these three issues here, right? Privacy, integrity, and authenticity. I hope everyone is clear with the goals that we are setting, the cryptographic goals. Now, as I mentioned, that most of you wouldn't even know how much crypto you use or how much crypto you rely on in your day-to-day lives. Okay, so let me give you some perspective. Let me give you a context. Everyone is familiar with Google, right? Of course, I think it goes without saying. Now, even as we are in this particular session is going on in a Google Meet, right? And we are accessing it via various browsers. Someone is using Firefox, someone is using Edge, someone is using Chrome. Okay, so we are using it through various browsers, right? Now, this session itself, what kinds of things can happen here and what are there in the background? Let's try to get some perspective. The first thing, even in this particular window, right? If I just go back here and I look here in this particular window, I can see that there is this lock here, right? There's a lock symbol here. So when I click on it, it shows me connection secure, right? Here it's showing me connection secure. So what is this? What does this mean? So let's try to understand. So you can see that here we are having this particular window of Google. So every one of I think we visit Google hundreds of times. We search so many things, right? So what we have here is this symbol, right? And it shows us that it's a secure connection. So this is important. As we just saw in the windows, it's a secure connection. And then what happens is we can see what is inside. Now, in this particular window, if you click on this button here, okay, this will give you a window like this. Okay, now this window may differ based on which operating system you are. This one is on Linux, okay, on Ubuntu. So on Ubuntu, if I open up this page was accessed before, it's an old screenshot. So you can see that it tells us that the connection is encrypted here, right? Here in below, it is telling us the connection is encrypted. And then it is showing us a big string here, right? Let's try to zoom in it a bit. So what is this telling? It is telling us connection is encrypted, and then it is showing us a big string. Okay, let's try to understand what does this string mean. Let's try to understand every term here: TLS, ECDHE, ECDSA, AES, GCM, SHA-256, right? Let us try to understand all these terms one by one. The first thing that we would like to see is it is showing something like ECDH. So what is this? So the full form of this term is elliptic curve Diffie-Hellman exchange. Okay, so it's basically a key exchange mechanism. Now I will tell you later what it is, but as of now you can understand that when you when you communicate with someone, there has to be some secret information between you and the other person. Okay, so when Alice is communicating with Bob, they both must have some secret information which Eve doesn't have. Okay, Eve will not have that information. Alice and Bob will have. So that is the key. That is known as the key. That key has to be exchanged, right? Alice and Bob must exchange the key. Without exchanging the key, how can they communicate? So that is the key exchange mechanism. So you see, even now when we are in this particular session or in a Google search, this key exchange is happening. What comes next? The next thing is ECDSA. It's a digital signature algorithm. So this algorithm actually gives authenticity. So we talked about this problem of authenticity. So ECDSA stands for elliptic curve digital signature algorithm. We don't need to understand what the algorithm is. Just try to understand what it does. What is the utility of this algorithm? It actually gives us authenticity. So it gives us a way to verify whether the person we are communicating with is actually that person. Here ECDSA ensures that when you are talking to google.co.in, is it actually google.co.in or some other website which is pretending to be google.co.in? Like in the Alice and Bob scenario, is it actually Alice communicating with Bob or Eve who is pretending to be Alice? That is what we try to find out using the digital signature algorithm, right? So this is another thing that is being used. And then we have GCM. GCM is an authenticated encryption mode. I'll not go into the details. It is something that gives us both authenticity and a privacy at the same time, two goals together. So I'll probably skip this in the interest of time. And then we have a hash function. So hash function, this is SHA-256. What does a hash function do? It solves the problem of integrity. That is, if some data is tampered, then we'll be able to detect it. If any of the information that is being exchanged between you and google.co.in, between your computer and the google.co.in server, If any information is being exchanged, if it is being tampered, then it can be detected. So the hash function is a way of ensuring the integrity of data. And then we have a block cipher. It's like AES. What does AES give you? AES gives you privacy. Remember, we want that Alice and Bob will communicate, and Eve should not be able to understand whatever they are communicating. For Eve is a question mark. What is going on here? But it is Eve knows that Alice and Bob are communicating. That is, it is not hidden, but she is not able to know what it is. Okay, so that protection is given by the block cipher like AES. AES stands for Advanced Encryption Standard. Okay, so you can understand that even without knowing anything about cryptography, maybe you are using cryptography every moment, at every second of your digital lives, that your digital living, whatever life you lead in the cyberspace. Okay, it is relying on the framework of cryptographic algorithms for various purposes, either to do a privacy, either to preserve privacy or integrity or authenticity, and among many other things. These are the primary goals. Okay, now I generally use this particular picture. It's a symbol of Chinese philosophy. It's known as the yin and yang. What it tells us is that the philosophy is that there is a duality in life. So this is good and this is bad. Okay, this is bad and this part is good, right? So this is the bad that is in good, and this one is the good that is in bad. Okay, and this entire thing tells us that this is life. So it's a duality between good and bad. So there is something good in bad, something bad in good, and the total thing is a dual. There is a dual nature. It's like they are related. Okay, they go hand in hand. So similarly, cryptography and cryptanalysis are two fields that have this dual nature. They go hand in hand. One improves the other. Okay, so cryptography is more of the design part, while cryptanalysis is more of the analysis part or the breaking part. So when someone tells you that an algorithm is broken or a cryptographic security is broken, then it's most probably due to the cryptanalysis that it has happened, right? And cryptography is more about designing ciphers, designing cryptographic algorithms that will give us authenticity, privacy, integrity. So I think up till this time we understand what cryptography is, what is the basic context of cryptography, and we also understand how it kind of is around us, all around us. It is we are surrounded by the world of cryptography. So let's move on and try to get a historical perspective of cryptography. Is cryptography very recent phenomena? Is it only that after the internet it has come? No. Cryptography has been there. It has played a big role in a lot of things, specifically for the developments, for the advancements in the field of computer science. Cryptography has a great role. If you know Alan Turing, if some of you have even seen this movie, if you have not read about the Imitation Game, you perhaps would know that how big a role cryptography has played in the evolution of the field of computer science, complexity theory, and other related areas. Okay, it's a very interdisciplinary field. So historically, cryptography has been there for ages. Even from the time of Julius Caesar, it has been rumored that there was this cipher known as Caesar cipher or shift cipher. Okay, and it's one of the earliest known ciphers. And what is the thing that this cipher actually did? So the thing was, it took a input and it would shift those inputs by a fixed amount of numbers. So for example, in this case, this is the Caesar cipher. It has got a shift of 3. Okay, shift of 3 means if D is at this spot, so a shift of 3 means D is replaced by A. Similarly, E is replaced by B. F is replaced by C. So this is a shift. So whenever you have a text, you take the text. If there is a D in the text, replace the text with an A. If there is an E in the text, replace the text with a B. If the F in the text, replace with a C. And like this, the entire alphabets, all the alphabets are covered here, right? It is, you can see the impression. It continues. So this is a very simple cipher known as the shift cipher. And it is one of the earliest knowns. And the shift cipher actually can have any number of shifts. So we have 0 to 25 possible shifts. 0 means no shift. 25 means Z, right? Z is coming to A. Z is replaced with A, right? we cannot have more than that, because if we have more than that, and it will wrap back to one of the previous ones. So there are these 26 possible shifts, right? And among these, this particular shift, the shift of 3, was used by Julius Caesar. Okay, so moving on, what is the mathematically, how can you capture it? So basically the wrapping back thing is captured through modular arithmetic. Okay, so modular arithmetic is something very known to all of you. It is nothing but the remainder that you get when you divide, right? So if I think of, like here, when I take this x plus k, I am doing mod 26, because when I add an x and k, it can become greater than 26, right? Greater than equal to 26. So whenever it becomes greater than equal to 26, it has to be brought back, right, to the domain, because here a represents 0, b represents 1, and z represents 25. So we have only 0 to 25 possibilities. It cannot be more than that. There is no letter corresponding to 26. So 26 is essentially 0. So because 26, mod 26 is 0. So mod means you divide by 26 and the remainder is 0, right? So you understand how many possible keys? We have 26 keys, right? So if there are 26 keys, okay, what is the situation here? Before that, what is the decryption? So encryption here means we are trying to transform the information from the original text to a new kind of text, which Eve will not be able to understand, that kind of a text, right? So for this, what do? You do an addition and you do a modular reduction, right? And you have to undo this. If it has reached Bob, how will Bob understand? Bob will have the information about K. This K is known to both Bob and Alice. Alice and Bob both know this K. Eve doesn't know this K. K is not known to Eve. So Eve will not be able to subtract, right? It is just that Bob can do it. But the problem here is there are only 26 possibilities. So even if Eve doesn't know the key, Eve can try out all the different shifts. Eve will use it 0, then 1, then 2, like this. Eve will try after 25. And of course, the key is among these possibilities only. So one of them will be the key, and Eve can break it, right? So this is the notion of brute force. So you brute force all the possible keys, and you can actually break it, right? Now, the next question is very important. Can we break it without guessing the key? This is very important. Can you break it without guessing the key, without brute forcing, right? And that is what is interesting, and we'll learn in the next slide that how we can break it without even guessing the key, right? So what if the key space is huge? This is the question. That if the key space is huge, it's very big, then this brute force attack will not be possible, right? Because brute force tries all the different keys. So this attack is not going to be possible if you have a huge key space. That is, the huge number of possible keys are there. In this case, it is just 26. That's why brute force is possible. But if it is 2 to the 100, then brute force becomes very difficult, right? So currently, the ciphers that we have give us protection like 2 to the 80 onwards. They will give us up till 2 to the 256, even more. Okay, so they are protected against brute force attack. Because brute force is a naive attack. It has no intelligence. It is just, you repeatedly try all the keys. Right. Now the question we are trying to answer, that without guessing the key, can we break it? And that will fall in the area of code breaking or cryptanalysis. Okay. And again, we just saw the historical perspective of crypto, which goes back to Julius Caesar and even maybe before, right? What is the historical perspective of cryptanalysis? What is the historical perspective of breaking a cipher, breaking an algorithm? We understand constructing an algorithm. Shift cipher is an algorithm, but what about breaking it? So the earliest reference goes back to Al-Kindi. Okay, he was a 9th century Arab scientist, Al-Kindi, and his texts were rediscovered in 1987 in Istanbul. Okay, and this is actually a page from his manuscript. Okay, the first page, and the title of the text was "On Deciphering Cryptographic Messages." Of course, it was in Arab. Arabic. It was in Arabic, but it translates to "On Deciphering Cryptographic Messages." Okay, this is the title. And you can actually, if you want, you can read about it in the History of Cryptography by Simon Singh. So what he did in this part was to break the crypto system, to break the encryption algorithm. The Al-Kindi observed that he could do something like letter frequency analysis. Okay, that means whenever you change something using an algorithm, like here in case of shift cipher, what we did, we replaced D with, we replaced A with D, like this, right? We did these things. We replaced A with D, and then we shifted it, right? Or we replaced D with A, sorry. We replaced D with A, and then we replaced E with B, right? So this thing we did, right? This replacement was our encryption algorithm. But can this actually preserve the input statistics? That is the thing. Can it preserve the properties of the input? Does changing D to A help us there? Actually, no. And we will see how. And this is one of the earliest reference of code breaking. Without even brute forcing the key, we can try to find out what the key is. Okay. And that is the idea of cryptanalysis. So this is a histogram which tells us how we can break the cipher without even knowing the key. By what? This uses letter frequency analysis. Means in the English language, which is the most common word, which is the most common letter? The most common letter is E. See this E. This corresponds to E. E's frequency is highest. Okay. Which is the next most common letter? This is T. Right. So what I can do is that if you use the Caesar cipher, okay, to encrypt a piece of text, what I'll do is that I'll try to find out which is the most frequent letter in that text. Hey, which is the most frequent letter in the text? I'll try to find out. So if I see that it is something like D is the most frequent letter, then I will guess perhaps D is E. E has been replaced by D. This is what we are trying to, we can guess, right? That is this by this analysis. So this is how so we are not brute forcing the key. We are doing an analysis of the cipher text. We are doing an analysis of the output. Cipher text is the output. So you have the input, which is your message. You have the shift cipher here, and you have the output, which is the cipher text. C. What I do is this, I do an analysis of like this on C and try to find out which is the most frequent letter. And since we know in English language, it is E, we can guess, we can make an educated guess that most probably E was replaced by the new letter, whichever is the most frequent letter, if it is D, right? So this is the idea of frequency analysis. So if anyone has any problem understanding, please try to interrupt me. There is no problem. I'll explain things again. And in between, I'll also ask you whether you got it. So you can maybe use the raise hand thing in your browser and tell me that you understood. So can everyone raise their hands if you got it? So I can understand that from the window that actually you got it. Okay, good. So people can raise their hands and I can understand that you got it. Very good. Thank you. You can lower it now. Once you have raised, you can lower it. Thank you very much. Okay, now there is another very important principle that we actually try to understand in crypto, and that is the principle of the Karshav's principle. That is known as the Karshav's principle. What is the Karshav's principle? So everything about a crypto system, everything about a cryptographic algorithm, except the key, is public knowledge. That means you actually cannot tell me that my algorithm is secret. Your algorithm cannot be secret. Your algorithm actually has to be public. But what is the secret? Only the key. So between Alice and Bob and Eve, everybody knows that Alice is using the shift cipher. Bob has to know because Bob has to decrypt the text. Eve should also know it's using the shift cipher, and we know how shift cipher works. But which key Alice has used is the secret. It is the only thing that Eve will not know. Key will be known to Alice, key will be known to Bob. Eve doesn't know the key. That is the only secret. So this is known as the Karshav's principle. There is another philosophy which tells us that the algorithm can also be secret. That is known as security by obscurity. We are not telling about that. That is not the model we are telling, right? So the only parameter is the key that distinguishes Bob and Eve. Bob and Eve are distinguished only by the fact that Bob knows the key, Eve doesn't know the key. That's it. That is the Karshav's. Please remember the Karshav's principle. Okay, good. So the next thing is I'll give you a rough taxonomy of what cryptography is. What are the various things that we have in crypto, the various fields? So as I mentioned, the mother is cryptology. We call it cryptology. Cryptology has this child cryptography, cryptanalysis and cryptography. We know that cryptography means you are designing stuff. Cryptanalysis means you are breaking stuff. Okay, so let's see what is there in cryptography. Okay, so in cryptography, there are various sub areas. One is known as the symmetric key cryptography. If Alice and Bob have the same key, then it's symmetric. It's called symmetric key cryptography. Okay, symmetric key cryptography. So they have the same key. Asymmetric means Alice and Bob will have different keys. Means the key that Alice uses to send the information to Bob is something. Bob uses a different key to decrypt the information, to undo what Alice has done. So that's why it's called asymmetric. Okay. Now, even in symmetric key, what we have? Various fields. The various fields are, one is known as block cipher. Okay. So in today's talk, we'll learn about block ciphers. So they are a special type of cryptography primitive that give privacy. So block cipher and stream cipher both give privacy. Okay. Hash functions give us integrity. In today's lecture, we'll also learn about hash functions. MACs give us authenticity. So we'll not be reading about MAC today, but in the second lecture, we'll understand how MAC, so we'll see an application of MAC. And then in asymmetric cryptography, we have various kinds of problems on which cryptography is based. Difficult problems on which cryptography is based, like factoring based problems, discrete lock problems, okay? And then there are digital signatures which give us authenticity in asymmetric cryptography. So in today's lecture, we'll also learn a bit about digital signatures. Okay, so these are the ways, and then we have cryptographic protocols, okay, which tells us how this communication should happen, what are the information that should be exchanged to establish something. But in today's lecture, we will not be working on protocols. What is the thing that happens in cryptanalysis? So in the cryptanalysis part, what we have is these various kinds of ways. One is the classical cryptanalysis. That means you do a mathematical analysis of an algorithm, right? What we did now, this letter frequency analysis, okay, and then there is brute force, which has nothing involved in terms of intelligence. It is more of a it's a automated thing. You try all the keys one by one and find out if the correct key is there. The second kind of cryptanalysis is known as implementation based cryptanalysis, which is like side channel attacks. Okay, that means you exploit the implementation, not the theory, but the implementation. You have a device that has some cryptographic algorithm embedded, and you exploit the properties of the device. Okay, that is like an implementation based. And then of course you have social engineering, which we come every day, phishing attacks where people want to get access of our computer and try to steal information. So these are like social engineering attacks. Okay, so this is roughly the idea of crypto, and as at a glance, the rough taxonomy. Okay, and this, I think this gives you a fair idea about the field of crypto. Okay, so crypto at a glance. Now we start our first problem today, part 1, that is symmetric encryption. So I mentioned that we will be working with symmetric encryption. So this is symmetric encryption, and we will be learning about block ciphers today. Okay, so we want to achieve privacy. It's symmetric because they have the same key. Alice and Bob have the same key. That's why it's called symmetric. Encryption gives us privacy. Okay, so encryption is a cryptographic primitive that gives us privacy. And encryption here we will doing through block cipher. So the block ciphers helps us achieve privacy. So what is a block cipher? This is one of my very favorite pictures. This pictures actually gives me the idea of block and stream. So you see here we have a brick. So block means each brick. So block means it's discrete. We are using some fixed length, right? These are all blocks. These are the bricks. So block cipher operates on data in chunks. Their data is divided into blocks, and on each block, the block cipher operates. On the other hand, if you look at stream cipher, this is this pipe. And in the stream cipher, in pipe will have something like water or sewage, whatever. But it's a continuous. It tells us it's a continuous flow. There is no division here in that sense. Continuous data is flowing. So stream ciphers actually give us this. So in today's, of course, our concentration will be block ciphers. Okay. So before we go, we'll give a rough idea about what block ciphers and stream ciphers will actually look like. So a stream cipher is like this. Okay, there is something known as a bit stream generation algorithm, which takes a secret input k. So we mentioned the secret input is k. So it is taking the secret input k, this bit stream generation algorithm, and it is generating a bit stream ki. Okay, and what you take the plain text and you do this XOR. I think everybody is familiar with the XOR operation. Okay, exclusive OR operation, right? Or sometimes it's also known as a symmetric difference. So exclusive OR means 0, 1 and 1, 0 will give you 1, while if 0, 0 and 1, 1, right, you get 0, right? That's the exclusive OR operation. So this gives you the ciphertext. You have a key, you have a bit stream generation algorithm, which generates a bit stream, and every bit, it's a bitwise XOR. So you take the bits of the plain text and XOR the bits of the ciphertext. Key stream and get the ciphertext. And at the decryption end, you undo this. So you do the XOR again. So you all know that XOR is a operation that can be undone by applying it again, right? So if I do X XOR Y and again I do XOR Y, then Y will cancel out and I'll get back X, right? You understand this? X XOR Y, again Y, right? We will actually get X. So this is the plain text. So we get back the plain text. We use the key again at the. So this is Alice's end. This is Bob's end. Eve is here. Eve is looking at the ciphertext, but Eve doesn't have the key. This key is not available with Eve, right? So Eve cannot understand what C is actually, while Bob can undo what Alice has done and see. On the contrary, if you look at this half, you can see that block ciphers are not operating in a stream. They are actually operating on a block, B bits. It is taking B bits of the plain text, applying an algorithm which takes the secret key as an input and gives the ciphertext, which is communicated to Bob, right? And what Bob does, Bob takes the ciphertext, applies the decryption algorithm, which is the inverse of the encryption algorithm, and gets back the plain text, which was used by Alice, right? But always operations are B bits. That's why you call block cipher. Okay, now going further into block ciphers, these block ciphers actually, what are the inputs they take? We just saw, right? What are the inputs they take? The first input they take is the message, and then they take the key and they provide the ciphertext, right? So input block is M, output block is C, key is K, and block length is N, right? What is the block length? That is how much data it can consume, right? It was B bits, here it is N bits. That's why we are writing that it's a mapping from 0, 1, N, right? So this is N bits, and you get N here. So 0, 1, N to 0, 1 mod K. Mod K means this size. This is mod K. This is the size of the key, right? And you get a ciphertext which is again mod N, right? This one. That's why 0, 1, N. You get a N bit string to an N bit string. So what are the features? That when you know the key, it is easy to encrypt or decrypt. So there is efficiency. If the key is known, it is easy to do this. Okay. If you have M and C, it is difficult to compute K. So given the message and the ciphertext, you cannot compute the key, right? On the other hand, if you know the key, then it's very easy to decrypt. This is known as the inversion trapdoor. Inversion means you invert the ciphertext. You get the plain text back from the ciphertext. If the key is known to you, then it's very difficult. If the key is not known to you, it is very difficult. That is very easy. If the key is not known to you, then it's very difficult to invert it. That's why it is known as the inversion trapdoor. Okay. And then deterministic decryption. That means when I take a M0, I encrypt it, and then I decrypt it. Is the same key. See, they are same here. I should get back M0. Okay, this is the thing. Today we will demonstrate this later. In the second half in applied cryptography, we will demonstrate how we are getting the key, and using the same key we can get back the plain text from the ciphertext. Okay, now let's look inside a block cipher. So again, I will ask everyone, is it clear up till this part? Please raise your hand, then I can understand if it is clear. Okay, I can see 1 or 2 raised hands. Okay, please ask me questions if you have problem in anything.
Sir, could you please once again tell about the brick
tell about
slide?
what? Last slide, this
brick
one?
slide. Yeah, brick
Yeah.
one.
Brick one, okay, brick slide. Yeah, sure. So basically the brick slide is telling us that block ciphers work in blocks. So these bricks, the bricks are in blocks, right? The bricks have a fixed size. So this is an analogy. The bricks are of fixed size, right? This is just a pictorial, what should I say, comparison. So these bricks are in blocks. Similarly, block ciphers work in blocks. It is either n bits or b bits. It will be maybe every block is 100 bits in size. Then the block cipher operates on 100 bits at a time. On the other hand, a stream cipher is continuous. It doesn't have a fixed size. It can be 1 bit, it can be 1000 bit, it can be 51 bit. Doesn't matter. It can be anything. But block ciphers have a fixed size. This is what it means. So does this clarify the question?
Yes, sir.
Okay, great. Thanks, Morley. Okay, so we are going ahead with the next part. That is, what is inside a block cipher? Means, can we design a block cipher? Is there a rule by which we can design a block cipher? Some methodology? Is it there? So we look at the structural aspect of a block cipher, right? So to understand this, we have to actually go back to a very important, interesting paper. There is the communication theory of secrecy systems, which was introduced by Claude Shannon. So all of you who have done some course in information theory, or you know about this, you must have heard about Claude Shannon. So in communication theory of secrecy systems, he actually came up with this interesting property known as confusion and diffusion. Okay, so basically what we are trying to mean here, that how can we get a encryption algorithm, how can you get a block cipher such that our information remains private, and all the conditions that we maintained here. What are the conditions? I'll go back once more. The condition, that is, it is easy to encrypt, decrypt. If given message and ciphertext, you cannot find the key. If the key is known, it is easy to invert, and then you get a deterministic. These properties are preserved, right? So confusion and diffusion are the properties, are the features that you need. Okay, so this interpretation, there are many interpretations of these concepts. This is by Massey. Okay, so let me read it out. The ciphertext statistics should depend on the plain text statistics in a manner too complicated to be exploited by the cryptanalyst. It is written in a very lucid manner. That means the statistics of the ciphertext, that is what output you get, should depend on the plain text statistics, that is the input, statistics of the input, in a manner. There, of course, one is derived from the other. There is no doubt about this, right? Ciphertext is derived from the plain text using the key. But the relation that develops between the ciphertext and the plain text should be as complicated, so complicated that it cannot be exploited by a cryptanalyst. So you are safe. Your privacy of information will be maintained, right? So I think you should be able to understand this, that the relationship between the ciphertext and the plain text should be complicated enough so that a cryptanalyst is not able to exploit it. Okay, so this is known as confusion. And what is diffusion? Each digit of the plain text and each digit of the secret key should influence many digits of the ciphertext. Okay, that means you have the ciphertext, okay, which you get as an output. So the plain text and the key, these two inputs you have, they should affect many bits of the ciphertext. So each digit, right, every bit. So by digit you can consider it's a bit. So if there are 10 bits in the input in the plain text, if there are 10 bits in the key, so we have total 20 bits, and then there are 10 bits in the ciphertext, then what it is telling is that every bit of the key and every bit of the plain text should affect many bits of the ciphertext. This is known as diffusion. Okay, and block ciphers are designed to provide sufficient confusion and diffusion so that no one can break it, so that Eve cannot break it when Alice and Bob use the encryption algorithm, right? So this is the idea of confusion and diffusion. So the next question is, how can one get confusion and diffusion? So confusion and diffusion are more abstract notions, right? They are abstract notions. So how does one get confusion and diffusion? How to achieve them in practice? So actually they are achievable by very simple operations. For diffusion, you can rely on permutations. So permuting bits. So there is one bit here and there is another bit below, and you are changing the location of the bit. So maybe 1 is going to 2, 3 is going to 4, like this. So changing the position of the bit, that is permutation. So that provides us diffusion. Okay, it can be at the bit level, it can be at the byte level. Okay, and it's a linear component. That means it's a component whose algebraic degree is 1, right? It's linear. It's linear in nature. So next is substitution, which gives us confusion. Remember, confusion is about making the relationship between ciphertext and plaintext complicated. It is achieved through something known as substitution, and substitution is provided by something known as an S box. What is an S box? S box is a substitution box. S box, no idea is very simple. It is something like an array. So for example, I have an array here, 1, 2, 3, 4. 4 positions are there. Okay, and I can put 4 values here. Okay, and for these 4 values, definitely I want to put it in a way that are limited by 2 bits. So here I can put 2, then I can put 0 and 3 and 4, like this. That means, and what is the index position? Index position is 0, 1, 2, 3. So this is an S box. What it means is, if the input is 0, output should be 2. If the input is 1, output should be 0. If the input is 2, if the input is 0, output should be 2. If the input is 1, output should be 0. If the input is 2, output should be 3. If the input is 3, output should be 4. So this is a substitution box. We are substituting the input with an output. Okay. So this is a 2-bit, because these numbers can be represented by 2 bits, right? So 0, 0, 0, 1, 1, 0, 1, 1. That is 0, 1, 2, and 3. Right? So, sorry, I should have done a mistake here. I have to give here 1 actually, not 4. Sorry. This 1. Okay. So this is limited to this. Right? So this is a substitution box. It's like a lookup table, right? Like an array. It's like an array. It's like a lookup table, and it's a non-linear component. That means its algebraic degree is more than 1. Okay, this is algebraic degree is 1, so the degree is 1, and here the degree is more than 1. Okay, greater than 1. So that means it is something linear component is something like y equal to mx plus c, like a line, straight line equation. While the non-linear component can be something like, you know, y equal to x square plus mx plus c, like this. So its algebraic degree is greater than 1, right? It's a non-linear component. Just an example. Actually, they will look different. So block ciphers will contain some combination of substitution and permutation. Okay. Though this substitution gives substitution gives confusion, permutation gives diffusion. These are the 2 ingredients that we need to design a block cipher, and these are the 2 ways we can achieve those ingredients. And every block cipher will have some combination of S and P, substitution and permutation. And however, exact form of S and P, exact construction of S and P will vary, greatly vary. But they will contain this at a top level. Okay. So let's see this example now. This is the present cipher. It's a very famous cipher, and it's a lightweight cryptography standard called present, the present cipher. So what does this present cipher have? You can see here very interestingly, it has got this S is the substitution box. This complicated looking arrangement is the permutation. This is S and this is P. Okay, so S and P, and this is the secret key being added, Ki, before it is going into S. Okay, and again it is repeating. Again S, again P, right? So substitution permutation is going on here. And this is the S box of present. It's a 4-bit S box. 4-bit means it will map from 0 to 15. Right? That these are the 4 all numbers represented by these 4 bits. So 0 to 15, here it is in hexadecimal, so it is 0 to F. So, and you can see it's a 1-to-1 mapping. 0 goes to C, 1 goes to 5, 2 goes to 6, 3 goes to B. It's bijective. 2 inputs cannot go to the same output. It is unique, 1-to-1. Okay. So this is the S box, and this is a actual cipher, actual cryptographic algorithm, present, which is used widely, and it's a standard also. So now let us see what is the basic strategy that these algorithms are following. Okay, the basic strategy is to iterate a function. That means you have a core function. There is a core function. Okay, so here you can see there is this core function f. Okay, so this is f, and you can see f is applied repeatedly. Again f is being applied, again f is being applied. So, and this is going on, dot dot dot, this is going on. So f is being applied continuously. We are using the key, secret key is being used in between. So this is the plain text. Okay, and later on when we go on, we'll get the ciphertext. Okay, so there is a function called f, which is known as a round function.
क्वेश्चन
It's called a round.
सेशन वाज वेरी गुड
Okay.
सर क्वेश्चन तो नहीं, पर एक लाइन में सेशन को समराइज करूं सर?
थिंकिंग ही अपने को आगे बढ़ने सही है सर।
I think
शेयर करना चाहूंगा
there is someone has unmuted.
सेशन का जो चार्जेस है सर बहुत हाई होता है, सही है
Mr. Piyush. Thank you. Okay. So, as you are mentioning that this function f is known as the round function. Okay, round function is the core function, is the basic function, and we use it again, we iterate it. Okay, so how you design f is the basic idea of designing block ciphers, designing the actual round function, and once you design the round function, you just apply it again and again. F itself may be weak, but f when it's applied multiple times leads to a secure construction. This is the idea. Okay, so you get a secure construction by applying f again and again. F is a round function. So there are various ways of designing f. One is substitution permutation network. This one, another is known as the Feastel network. These are two ways of designing the function f, this function f. Once you design f, iterate f. That is very simple, iterating the function. But designing the core function is the basic job that we need to do. So let's see this. These are two ways. On the left hand side, you have the Feastel structure. On the right hand side, you have the SPN. SPN stands for substitution permutation network. AES is an example of SPN, while Feastel's example is DES, which is the data encryption standard, which is the predecessor of AES. Before 2000, when AES was brought into the scene. So, how do they differ, this substitution permutation network and this Feastel structure? If you look at this, in Feastel, there is a message which is split. The message is being split in two parts. This is one line, this is another line. Message is split between two parts, then it goes to a round function, and it is rejoined with the another part, and then it is sent here. So there is a swap operation here. This half goes to this half, this half goes to this half. And then again, the same round function is being repeated, right? The same concept. There is a round function and you apply the round function again and again. The only difference in Feastel is you divide the state. While in case of this substitution permutation network, you are not dividing it. You are adding the key, doing substitution, permutation, then again adding the key, doing substitution, permutation, again adding the key. So this entire thing is a round. This entire thing is a round. This entire thing is a round. Okay. So you are applying rounds again and again. Same round is being again and again. Of course, the keys are used differently, separately. So this is the idea of substitution permutation networks and Feastel structure, right? Now let us see what we talk when we talk about this key. What is happening there? KS. We have used this name KS, right? So in today's lecture, we will be concentrating on substitution permutation network. So this KS, right? This is actually known as the key schedule. Key schedule or the key expansion algorithm. Okay. So what does this do? It actually generates from the main key, the key that is exchanged between Alice and Bob. So remember, Alice and Bob have the same key. It's a symmetric encryption. Alice and Bob have the same key. So the key that was exchanged between Alice and Bob, that key is actually being used in this key schedule algorithm, the input of the key schedule algorithm. And what it does is that for every round, it generates a sub key. It is a key derivation. So here it will be K0, K1, like this, Kn. It will generate all the sub keys. Okay. So you take one key and derive sub keys from that key, and that is being done by the key schedule algorithm. Okay. For some algorithms, it is very simple. The key schedule is very simple. For some, it can be very complex. Okay. So for AES, it is a bit complicated. For present, it is comparatively much simpler. Okay. So this is the key schedule algorithm. So let us summarize what we have learned as of now. We understand what a block cipher is. It operates in blocks. We understand that there are two fundamental ingredients, confusion and diffusion, that is needed to design a block cipher. We understand that confusion is being taken from substitution operation like the S box. On the other hand, diffusion is being taken from the permutation operation, which is the permutation layer, right, which we saw in that cipher present. And then we have this idea that there is a round function which is designed using substitution and permutation, like you can see here. This is a round function, and then it is iterated again and again. So you can see it is used again, it is used again and again to make the entire construction, to make the complete construction, this full construction. And then we have the key schedule algorithm, which actually takes the master key that is being shared by Alice and Bob and derives sub keys from there and sends it to every round. It is going to every round. The sub keys are going to every round. So this is the idea. This is what we have done as of now, right? So we get a generic idea of a block cipher and its iterated structure. We understand there are two common design techniques like Feastel network, where the message is divided in two parts and then processed, while substitution permutation networks, it is not divided. Okay, but remember, it always this processes B bits at a time. It's a fixed size that it processes. That's why it's called a block cipher, right? Now the question might come to your mind that if it only processes B bits, what if I have a information that is bigger than B bits, right? How will I encrypt it, right? So the idea is kabhi mat bhul, divide and rule, right? So you divide and rule. You divide the input into chunks. So for example, I have a 128-bit block cipher. That means it can process 128 bits at a time. But what I have is a 138-bit plain text. This is the key size. This is the block cipher size, the block size. Okay. So the block size. So, and I have 138-bit plain text. The problem is it is greater. So what I will do is that I will take 128 bits, and for the next 10 bits, I'll take it in another block and pad it. Because I have to keep it in a multiple of blocks, right? It processes B blocks. I can't process 10 bits. It has to be 128 bits. So I will add more 118 bits here to make it 128. This is known as the padding bits. Padding. So that the size becomes 128. So this will also become 128. Now I process this block and this block. And then I will combine them. That is known as the mode of operation. How are they combined? When I process the two blocks together, are they separate or they will be combined? So they can be separate also and they can be combined. So this is known as the mode of operation. Okay, how to combine separately processed blocks. So let's see here the mode of operation. So there are various kinds of mode of operation like the ECB, electronic code book mode, which tells us that the blocks should be separately processed. If you have this block, if you have this block, this is plain text 1, this is plain text 2, and you get ciphertext 1, ciphertext 2, and transmit this to Bob. Alice transmits ciphertext 1 and 2 to Bob. That's it. C1 and C2. So you do C1 concatenated in C2 and send it to Bob. That is electronic code book mode, ECB. Okay. While all the other blocks combine C1 and C2 in some way. Okay. Or they process them in some way. So some way of combining them. Okay. I'll not go into the details, but we will discuss one small part. So here I show you a limitation of ECB mode. See, this is the Linux Tux, the Linux Penguin. Okay. And you can see this encryption is using ECB mode. You can see here the structure of the Penguin is preserved, right? Because it is doing block by block. So the boundary of the Penguin, this boundary is actually not affected. The boundary is still preserved. Though the color has changed, everything else has changed, the boundary is preserved, right? This is ECB mode. On the other hand, this is known as CBC mode, which is not independent. The blocks are not independently encrypted. You see, it is completely randomized. You can't make out anything from it. That's why ECB is dangerous. So you need to do this kind of randomization. There should be dependency between instantiations, right? Between blocks. So here I will give only a small example of CBC mode. It's a very simple mode. So this is the first plain text block, the second plain text block. So what you do is that before you apply the encryption, after you apply the encryption algorithm, okay, before you apply it, you apply one random number here. And along with the message, you encrypt it, and this is the ciphertext. And the random number is known as C0. Okay, so just think about it. The ciphertext is again fed back to the next block here, and then the message, second message is coming down. It is being XORed. It is being fed back, and this is how C2 comes, and this continues. That's why it is known as cipher block chaining. you are chaining the blocks like this, you are chaining the blocks, right? So all blocks that go forward are dependent on the previous blocks. If anything changes in the previous block, forward everything is going to change, right? And similarly, the decryption proceeds in the same way. Okay, so you have to send this extra bit of information C0, which is the random number. It's a IV, it's known as IV, initialization vector, IV, which is like a random number that is generated for the first insert. This is known as CBC mode. Okay, so as of now, I will ask a question that whether all the participants have understood what we did. So please raise your hands if you understood what we have done up till now. Okay. Okay. Fine. Thank you. I can see most of you got it. Yeah, very good. So now the next thing that we are going to see. So what we did, let me summarize once more. As of now, what we have done was we have tried to solve the problem of privacy. Okay. How it was solved? It was solved using block ciphers, using symmetric encryption primitive known as block ciphers. And what do block ciphers give us? What is the thing that we achieve through block ciphers? We get a way of achieving privacy using two ingredients, confusion and diffusion. And confusion and diffusion are achieved through two operations, permutation, substitution and permutation respectively. And then we saw that there is a way of combining them using a round function in the substitution permutation network mode. And then there is a key schedule. And after that, we saw that since we have to process arbitrary amount of data and a block cipher only processes B bits at a time, we have to divide the input into blocks of B bits. And the last block, if it is a multiple of B, it is very good. If it is not a multiple of B, we have to pad it to make it a multiple of B. And we will process all the blocks through the cipher, either independently if it is ECP mode or using CBC, CFB, other modes where we actually combine them one with the other. All the blocks are dependent, they're not independent. All blocks become dependent. Various way of combining. One is CBC, what we saw, right? So this is our basic takeaway from the first part. In the second part, we will look at the second problem, the problem of integrity, achieving integrity. That is, data should not be tamperable. One should not be able to tamper data, right? And this particular technique that we will rely on, the cryptographic primitive that will help us achieve integrity, is known as the cryptographic hash function. Please remember, I have not used the term only hash function. I have used the term cryptographic hash function because general hash function and cryptographic hash function can be different. They share some properties, but cryptographic hash functions need different properties, different other restrictions to be followed to make them a good cryptographic hash functions. So they are also known historically as modification detection codes. So they detect modification and they have some relation with coding theory. That's why the word codes comes here. So what is a cryptographic hash function basically? So if you look at this particular picture, you can see that it's a many-to-one mapping. Cryptographic hash function is actually a many-to-one mapping, right? You have an input space that you see here on the left and a hash space on the right. So the input space is huge, while the hash space is limited, right? So this is the idea of a hash function. It's actually a one-way function. Okay, so you map a larger input space to a smaller input space. That means there will be many inputs which will have the same output. It is not like the S box we talked about. S box was one-to-one. It is not one-to-one. It's a many-to-one mapping, right? So the first thing is, let's talk about hash functions in a application perspective. That where are they used? Actually, the hash functions are known as the Swiss Army knife of cryptographers. It has got lot of use in cryptography, the hash functions, and they're used in so many contexts. For example, they are used in digital signatures, okay, which we'll learn about in today's class also a bit. So digital signatures, hash functions are used. They are used in public key encryption. So in the second half, we will learn a bit about public key encryption. And then they are used for integrity verification, which is the current topic that we are discussing. How to verify if the integrity of data is maintained and how can you use a hash function for that. They are also used for message authentication. That means they will be used for finding out whether the message has originated from the authentic source, from the source it claims to have originated. Then they are also used for password protection. Today, in a practical example, we will see how Linux stores our passwords, how Ubuntu stores our password, and how it is maintained, how hash functions are used there. And then they're also used in key agreement protocols. So key agreement means when Alice and Bob will try to exchange the key, they will try to agree on the key. That is the key agreement protocol. Okay, and many other protocols. They are not. They are like, as I mentioned, they are the Swiss Army knife. So hash functions actually means they are one of the most versatile of all the crypto algorithms. Okay, and I'm very excited to share the idea of hash functions with you in whatever time we have left. So the next question that might pop in your mind that, okay, have I used a hash function anytime in my day-to-day use? Okay, and actually, undoubtedly, you have used it. You don't know about it definitely, but you have used it. So for example, whenever you connect to any HTTPS site, okay, you might have used your bank website, right? You might have logged onto online SBI. Okay, you have done a Google search, right? It's an HTTPS site. There is Hypertext Transfer Protocol secure. S stands for secure. So whenever you connected to HTTPS site, you have used a hash function, right? I have shown you in the example during the start of the talk. And then remote, you have used it for, if you have used SSH or IPsec, you have used it. If you have done some kind of intrusion detection analysis, you have used it. In IDS systems, it is used. Then forensic analysis, it is used. In Bitcoin, if some of you are interested, I know many of you might be interested in Bitcoin, proof of work, hash functions are used. In revision control systems like Git, I think many of you would be knowing about Git, or GitHub at least, which uses Git. Okay, they use hash functions, and the list goes on. So I am sure you have used either one or more of these, but most probably you have used the HTTPS, right? You must have used it, right? So this is the basic place where actually I think you might have used a hash function. Now, as I was mentioning, in a digital signature context, how does hash function come into the picture? Okay, so what happens in a digital signature is there is a key known as a secret key, and it is used to sign a message. Okay, this is an algorithm. Signature is an algorithm. Let's not go into the details how the algorithm works, but it's an operation known as signing. So just think there is a message, and the message may be 1 terabyte in size. That's a huge message, right? If I directly apply the message to in this signing, it is going to take a lot of time. So what instead I will do is that I will hash the message. The hash size will be something like 160 bits minimum, acceptable today. So 160 bits, then signing 160 bits is much simpler and efficient, right? So this is how hash functions, because as I mentioned, hash function use a larger space and maps into a smaller space, right? That is the job of hash function. So you take your message, which in this space, you apply the hash function, and you get the hash output here, which is smaller in size, and then use it in this algorithm. That is the idea of digital signature. So this is more an overview. I'm not going into the digital signature algorithm itself, but what it tells us is that this hash acts as an identifier for the message. Of course, it's not an unique identifier, because we know this is a many-to-one function, right? So there are many messages which will have the same input, right? There will be many messages which will have the same output. Sorry, many messages which will have the same output. Hence, it is not a unique identifier, but it's a identifier of the message, right? So this is the idea why hash functions are used in digital signature. I think the efficiency aspect you should be able to appreciate from this picture. Now, as I was mentioning, you should not confuse cryptography hash function with non-cryptographic hash functions. I think most of you might have encountered hash functions in the form of hash tables in data structures. I would expect that you would know about hash tables. But hash tables, the requirement of hash tables is not the same of the requirement of hash functions. Hash functions have a different kind of requirements, though both of them can have the same purpose in terms of what they do, reducing the input to a smaller output space. That might be same, but they are not using the hash. They are not. They have some additional requirements. Okay, so there is no notion of security in non-cryptographic hashes. That is the problem. In non-cryptographic hashes, there is no notion of security. There's only the notion of that hashing, collision will happen. They want collisions to happen and all those things. But here we have different requirements. So let us look at the requirements. So again, we are going back to that picture. First of all, it's a symmetry key primitive. In today's discussion, we are limiting ourselves to symmetry key in this particular talk. And its input is variable length, as we told. It's an arbitrary length input, right? But the output is definitely fixed. Okay, and it's called the hash or the digest. Recently, not that recent, maybe it has been around 5 years, I guess. Recent in cryptographic terms, maybe. So recently, there is a notion of variable length output as also. Output can also be variable. That is a recent development. So recent algorithms, cryptographic algorithms, also allow for the output to be of different lengths, varying lengths. Okay. So what are the extra requirements that we have? We'll learn about that. In this particular diagram, you can see the unpredictability of hash output. What do you mean by unpredictability? This is the output of a hash function SHA-256 on the character A. So the character A, when you do a SHA-256 of character A, you get this output. On the other hand, when you do SHA-56 on the character B, this is what is the output. You can just have a visual verification that these two outputs look very different. They don't look similar in any way. There is no pattern you can find by looking at them that, okay, this is something they are equivalent or this is equal, something like that. Right? This is known as the avalanche effect. So what I mean to say is that even if you change any bit in the input, small change in the input, then also the output will change in a great way. It will almost flip 50% of the bits in the output. That is the ideal case. So if you flip one bit, flip any bit in the input, the output will be flipped by 50%. Okay, that is a standard case. You can actually go to this website. Later on when I'll share the slides, you can take this website and find out about the hash generator and play with it. Now, what are the security notions of hash functions? How do you analyze them? Because we said that these hash functions are not the same as the hash functions that we had for what should I say? The non-cryptographic hash functions, right? The first thing is known as the pre-image. That means if you are given the output, there is a hash value, you should not be able to find the message from the hash value. This should be difficult. Okay. Second is known as second pre-image. That means I am giving you one message. I am giving you you can calculate this hash value. You have to find another message such that this is not equal to this. That is, there is a distinct second message you have to find. But here I am giving you the one message and trying to find out another distinct image. That is known as pre-image. The last and the most popular is about the collisions. Collisions means you have x not equal to x dash. That means you have to find two distinct messages such that their hash values will match. So what is the difference between this and this? Here you are given a message. Here you are not given this message. You are free to choose any message, any pair of messages. That is the difference. And this is the idea of collision. So collisions means, for example, if A's encryption, if A's hash would have given 123B and then Z's hash would have given 123B, then this is a collision between them. Basically, the same output is coming for A and Z. So that is a collision, right? And all these tasks should be hard to be solved for a good hash function. That is the idea that we have. Okay. So now let's move on to see how hash functions are designed. Like we saw how block ciphers is designed, how hash functions are designed. So there are two parts of hash function. One is known as the internal transformation, and like the block cipher is known as the mode of operation. Okay. So this internal transformation is actually a fixed length transformation. Like the block cipher, in a block cipher we have the internal structure as a fixed length, the block cipher as a fixed length, and then we use the mode of operation to combine to handle arbitrary data. Similarly, in case of hash function, the internal transformation will be fixed size, and the mode of operation is going to take care of the arbitrary length input. So internal transformation can be of these types. It can use a block cipher also as an internal transformation. It can use a compression function. Compression function is something like this. The input is, for example, 2n, the output is n. So it compresses the input. So it's a compression function. Okay, that is why it's called a compression function. The input is compressed and you get a smaller output. And you can also use permutations, right? And for the mode of operation, it iterates the internal transformation. So you understand this is iterated by this. You iterate it again and again by the mode of operation, right? And then that's why it's also known as the domain extension algorithm, right? So the mode of operation is the domain extension algorithm because it extends the domain of the algorithm. So now the next thing, this is actually a slide from my PhD thesis. So this is a taxonomy of hash designs. There are various ways of designing hash functions. Okay, these are some ways of designing. It can be iterated, it can be construction methods. In iterated, it can be Merkle-Dambert. This is one of the most popular hash functions which are currently in use. And sponge construction is the new type of hash function that currently has been introduced. Okay, these are two different ways of designing hash functions. I'll not go into the details of how we design them. It will take a lot of time, but from our current context, we can understand that there are two basic ways here, two important ways. One is the MD or Merkle-Dambert construction, and the other is the sponge construction. So we will possibly look only on the sponge construction today, how it looks like. So this is the sponge construction. I was talking about the internal transformation. This is the internal transformation. So this is the internal transformation, F, and you see it is applied again and again, F, again F, again and F, unless the entire data is consumed. So the data is again padded, this is the padding, and it is fed block by block to all the intermediate steps. Okay, so it is this is the idea of the absorption phase. So absorption means you take the entire message, finish the entire message. After the entire message has been absorbed, we apply another iteration of F and then start taking the output. So this is the output. It is going out from every branch. And as I mentioned, there is a 3 dots here, means it's a variable length output. You can take variable length output. You can apply another F, keep on applying F unless you are satisfied with the output length, whichever output length you want. And this is known as squeezing, absorbing and squeezing. And that's why it's known as sponge, because the sponge absorbs water or a liquid and then you can squeeze to take out that liquid, right? This is the analogy. That's why it's known as a sponge construction. It absorbs the data, then you squeeze out the hash. So what is a real world example of this? A real world example of this would be hashing in Git, like the GitHub. I think many of you might have used Git. So in Git, actually what happens is all the structures inside, the way Git finds out that there are multiple files of the same type, there are same files which are used multiple places. So if you have a big software, it might happen that two people are using the same copy of a file at different places. What Git does is that Git tracks it using hash values. So because the hash value of a particular file will be unique. Not unique, I should not say what the unique, it acts as a unique identifier of the file, even if the file is copied. So you have a F1 file, it has got some H, and then you copy to F2, its hash value will also be H. Okay, so using this hash function, it finds out whether there are duplicate files in the system. If there are duplicate files in the system, it doesn't store it again, it doesn't copy it. It does maintains a reference to this file. Okay, it is not copying, it is adding a reference to this file via this file, because this file is already there. The contents are same for these two files. So this is how it is using it is making the structures inside in the Git object model. So you can see every object is identified through hash value. Okay, so here this is not given totally, so this is the hash value. This is the hash value, which is given in dot dot. They are not telling it's a 168 bit, uses SHA-1. It's a 168 bit hash. So using the hash value, you can actually monitor all the files in your system. Okay, so this is the real world example. So now, if I want to summarize what we have learned as of now, in the hash function part as well as the block server part. So in the hash function part, we came to know that we are talking about integrity, data integrity. Okay, we are trying to solve the problem of integrity. It is solved through hash functions. Even if a single bit in the output is changed, the hash value is going to change, right? We understand the avalanche effect. So even a single bit is changed, the data is going to hash value is changed. So if I receive some information along with a hash value, and I can verify whether the information that is reached me, by calculating the hash value, that whether it is the same that it was supposed to reach me, then we actually get this. Using the hash function, we can verify it, because if a single bit is changed, the hash value is not going to match, right? This is the idea of hash functions. So hash functions try to solve this interesting problem of integrity here, though hash functions are used everywhere in all the different cryptographic settings. Hash functions play a very big role, but in this particular case of integrity, they are used to find out tampering or modification of information. And with that, saw that hash functions can be constructed. There are two parts. One is the internal transformation, another is known as the mode of operation. Internal transformation essentially handles the data itself, while the mode of operation will try to handle one fixed length data, and mode of operation will try to extend it to arbitrary length by iterating like before. And you have to do padding, whatever is there like before, like in case of the block cipher. So that was the idea of these hash functions and how they achieve this. And then we found out that there are various ways of designing hash functions. We saw there are two names, Markle-Damgard and Sponge. These are Markle-Damgard is of historical importance. Sponge is a recent invention. And we saw how Sponge works. We saw that there is this how the data is divided, and then how it is combined. Okay, and finally it is squeezed. So there is the absorption phase and squeezing phase. So in absorption phase, you actually take the input, you absorb the input. In the squeezing phase, you absorb out the output, squeeze out the hash value, right? So we understand this construction, and finally we saw a real world application through Git. Okay, so this is the basic thing. So what is the final summary here for this part? That we have introduced ourselves to cryptography. We got a basic introduction. We understand what is symmetric encryption, that Alice and Bob use the same key. We got some idea about block cipher design philosophies, how they are constructed. Okay, what is the idea of a mode of operation to work on arbitrary data. Next part, we came to cryptography hash functions, and we understood what are the security notions of hash functions. So we had these three notions. One was pre-image, which is the one-wayness. That is, given the hash, you will not be able to go to the hash value, not go to the message. Given the message, you can always come to the hash value, which is the one-way property. You can go in the forward direction, but going in the backward direction is very difficult. So this is the pre-image. Then we understood second pre-image, which is a modification of the pre-image setting. And finally, we saw the collision, which is a very important setting, where you have to find distinct messages which have the same hash value. We know that this exists because it's a many-to-one mapping, but we don't know how to find it. That's why it is difficult to find collisions. And then we looked at some hash construction like Sponge. Okay, now before concluding this session, I would like to tell you about the lab we have here. It's called the Deciphered Lab, which is the cryptography and computer security lab here. And we have collaborators from various places. This is our lab logo. And we are essentially a group of crypto enthusiasts. Okay, and we have people from ISI, TCS Innovation, and also from abroad, France, Singapore, and Warwick, UK. And we have joint projects with Delhi, IIT Delhi, and CDAC. Okay, currently we are focusing in these areas. I think Dr. Shukla also mentioned in the introduction. These are our areas: lightweight cryptography, fault analysis, automated analysis, and also quantum cryptography is something we are recently interested. And this is a picture. This is not very updated. We have new members. Some members have actually also passed and have joined foreign universities in the industry. Some of the lab members are here. And we also have many positions. So if in your institute or anyone you know is interested to do an internship or take up project positions, advertisements are done in the institute website. You can also mail us at this mail ID, or also mail me personally. My mail ID will be given later. So all these positions are available. And I'm concluding this first part by using this picture, which is actually the permanent campus photo. So we'll be actually moving closer to Bhilai at that time. So our permanent campus is coming up. Maybe in 1 year we are going to move. So I thank everyone. And I think once again, I'll just do a small survey that if people got what has been discussed in the second half, part 2. Please, if possible, raise your hand so that I can understand if you got the idea of hash functions in general. Anyone? Or shall I consider that, okay, everybody got it? Okay, I can see some hands raising up. Thank you. Thank you very much. Thank you very much. Okay, then I think this will be the last slide for this session, and I think we'll be taking a break. Dr. Shukla, we are taking a break, I guess, for 15 minutes.
Okay. Thanks for explaining this basics of cryptography in very nice way, and or we can say in a very simple way. In very simple way, you have covered the topics that mathematical perspectives and cryptography, symmetric, asymmetric cryptography, digital signature, hash functions, and I personally feel that all of we are just stuck with our chairs. So your way of presentation is very impressive and very attractive. Thank you. So,
okay. So we'll meet
there's
in
a
15
break of
minutes.
15 minutes.
Fine. Okay, thank you.